So I had a couple of questions in the break that were sort of, are you going to cover all of Monte Carlo methods? And the answer is no. I have an hour and a half. But you are going to hear a lot more in future talks about more advanced things. So I'm just trying to get everyone to the same level. If you've used Monte Carlo methods before, you might not see anything new in this talk, and you might want to check Facebook or slip out or do something else. Back to what we're looking at. So the basic Monte Carlo question is we want to estimate an expectation. We'll have a complicated distribution. We might not know that distribution, except we might not know the normalization constant of that distribution. And it could be something complicated and non-standard. If it is standard, if it's a Gaussian distribution or a uniform distribution or something like that, then we know how to sample from it. And the correct answer to how do I draw samples from this standard distribution, a gamma or a beta or a Gaussian or uniform, is use the existing routine in SciPy or Matlab or R or GSL or whichever package you're using. I have not had to implement very many sort of basic random number generators myself, and neither should you. But if you're curious, there is good stuff online that describes how a lot of them work. So this is a book where there's a scan free online, it's out of print, that describes sort of how the guts of a bunch of these random number generators work that you might use in SciPy. And it's also worth knowing a couple of the basic methods, or at least sort of the big picture of them, because more advanced methods take some ideas from them, or it sort of gives you some intuition as to what you can and can't do easily. So, for example, I think it's worth knowing at least a way of drawing from an arbitrary discrete distribution. So you usually have a function called rand, which will generate a uniform random number between 0 and 1. It's called rand in Matlab. It will be called slightly different things. I think it's random in numpy.random. So you want to turn this number u, which is between 0 and 1, into, say, a discrete label a, b, or c, where b has probability 1/2 and a has probability 0.3, and so on. So the obvious way of doing this is you arrange your discrete variables on a stick, and that stick has length 1 if the width of each segment is equal to the probability of the outcome, because probabilities add up to 1. You then get your random number u, and that gives you a position on the stick, and you read off which variable is at that point on the stick. So that's incredibly easy to implement. It's what I do most of the time. And amazingly, it's incredibly suboptimal. So if you're in a situation where instead of having 3 variables, you have thousands, and if you need to draw many, many samples from this distribution, this algorithm takes way too much compute time, and its big O complexity is much bigger than you need. So if you read this book, there's a really cool algorithm for sampling discrete distributions that's asymptotically much more efficient than this. I've implemented it, and I've never found it useful. But if you want to sample from really big distributions, then that's the way to go. The continuous version of that with probability densities is much the same. So in red, you've got a probability density over a real-valued distribution y. I've stolen this figure from Chris Bishop's book. H gives the cumulative distribution function, so it's just the running integral of the area under the red curve so far. And that blue curve goes up to 1 because the area under the curve is 1. So you've got the y-axis here, and I shouldn't call it the y-axis because this is the y-axis. But anyway, the vertical axis goes from 0 to 1. You draw your random number between 0 and 1. You read along until you hit the blue curve. You go down to the axis, and you read off your variable. So that's how to sample from an arbitrary real-valued distribution in 1D if you can do this integral, if you can get this blue curve. And it's pretty rare that you can actually do that integral. There are only so many integrals we can do in closed form. So for example, even if you have a gamma distribution and you want to sort of get that integral and invert it, it's a bit tricky. And that isn't what the gamma rand function in Matlab will actually be doing. So the way gamma rand and various other random number generators work is with the following intuition. If you've got a probability density, one way of reading off samples is you draw points at random from the area underneath the curve. So the black dots are darts thrown at random at the area underneath the blue curve. You then read off where they are on the axis, and those are your samples. So that's a general way of sampling from the distribution. The probability of landing in some thin region is proportional to the height of the curve, so it's proportional to the probability distribution, so you're doing the right thing. Okay, how do you draw the black dots from under a curve? Well, if that curve has a funny shape, then it might not be obvious how to do that. But there's this neat idea called rejection sampling that makes it pretty easy in some circumstances. So I've got a blue distribution I care about. I want to draw points at random from underneath this funky shape, and I don't know how to do it. So instead, I draw an envelope over the shape in red, and that envelope could have a standard form, like it could be a Gaussian or it could be a big uniform distribution. And I do know how to draw samples from underneath that. So rejection sampling says, draw points at random from underneath the envelope, underneath the red curve, throw away all the points that don't happen to be in the right place, that aren't underneath the blue curve, and the ones that are left are ones you can use. And then you read off their positions and you get samples. So rejection sampling is an idea that's worth knowing about. When I showed you this picture of how linear regression works, I hinted at rejection sampling there. I said, here are a bunch of samples from my prior. And then I said, here are samples from the posterior. You can think of those as drawing samples from the prior and throwing away the ones that don't fit. And if you went to Christian Ribert's ABC tutorial, you can see the sort of influences of this rejection sampling idea in a lot of algorithms. You might be surprised to know that rand n in Matlab, the code that generates Gaussian random variables, actually uses rejection sampling. So there are lots of ways of sampling from Gaussian distributions, and when you read textbooks, they tell you about the Box-Wheeler transformation and all these technical things you can do. But actually, if you want to write fast computer code and do stuff with bits quickly, the way to do it is to very carefully construct a nice piecewise constant steppy envelope over the Gaussian curve and use a heavily tuned rejection sampler, and that's what Matlab and many other libraries use. It's the fastest way I know to draw Gaussian random variables. Okay. We're not actually always interested in drawing samples, though. If I'm drawing a simulation, I'm going to simulate neutron scattering, or I'm going to simulate some process, then I might need to draw random steps from a particular distribution. But if I'm interested in solving integrals, then I might not care so much about what distribution I draw my samples from, and all of these light gray points I've thrown away seems like a waste of computation. If you ever compute something carefully and then just throw it away, it seems a bit wasteful. So importance sampling you can look at as a sort of less wasteful way of sampling from a distribution that you know how to sample from. We take an integral, and what I do is I take this integral that I actually want to compute, and I multiply by q, and I divide by q. So all I've done is taken the original integrand and multiplied by 1. So I haven't changed anything, as long as q is never 0, where the original integrand isn't 0, because then I've divided by 0 and bad things will happen. So this equation is always true as long as q has support wherever the integral has support. As I've colored in blue, the integral on the right is an expectation under q. The original integral is an expectation under p, and really the integral on the right is still an expectation under p. But you can also view it as an expectation under q. So I can apply the simple Monte Carlo idea to this integral. I can draw samples from q and evaluate the rest of the integrand under those samples. So my original integral could be under some complicated posterior distribution that I don't know how to sample from. Instead, I sample things from a Gaussian, which I do know how to sample from because MATLAB and R and SciPy give me functions to do it. So I draw parameters of my model from that Gaussian, and then I evaluate everything using those samples. And so now I can compute any integral I like by just drawing samples from standard distributions. There's a small caveat here which you might have noticed. If I sample from p here, the p disappears from what I need to compute. But because I'm sampling from q here, the p hasn't disappeared. So I'm going to have to compute p in order to compute this sum. And often the distribution we're interested in, we don't actually know all of it. We don't know the normalizing constant. I normally say the distribution I'm interested in is proportional to all this stuff, but I don't know what the normalizing constant is. So there's a version of importance sampling, a version of this algorithm, where you don't actually need to know the normalization of P. This thing here, P over Q, is called the importance weight. It's the ratio of the original distribution you cared about and the one you're using, and it's used to weight the samples. So if the distribution you're interested in is actually much bigger than the distribution you used, that sample has greater importance and you should weight it more because you don't visit that place as often as you should when you sample from Q. In the other version of importance sampling, the importance weights you use unnormalized distributions. So the star here means I've evaluated these things up to some constant, and that thing is called the importance weight. And the way the algorithm works is very simple. I've decided not to step through the proof, but the details are in the slide for if you go over it. So you get this unnormalized importance weight and you normalize them. So you make all of these weights add up to 1, and then good stuff happens. So you can run the importance sampling algorithm and you still get a sensible estimator of your integral without needing to be able to normalize any of the distributions. Technically, this thing is biased. What that means is, on average, you're not going to get the right answer. Oh well. But it's consistent. If you draw a load of samples, you'll tend towards the correct answer. And I don't always worry about things being biased. As long as it's going to be close to the right answer, that's the important thing. OK, so the summary so far is Monte Carlo is just a fancy term for draw samples and see what happens, and that's often a good thing to do. And you can also compute integrals with samples. If you want, you can draw samples from any distribution using rejection sampling, but that's a bit wasteful if you only care about the integrals, so we do this importance sampling trick instead. So you get any integral you want, you multiply by Q, you divide by Q, you draw samples from Q, and then you've got an estimator. And all of that works if you have a small model with a couple of parameters, if your integrals are only in a small number of dimensions. But you run into serious problems if you're doing sort of real data analysis on interesting models for high-dimensional problems. So I've got a little toy set up to demonstrate part of what goes wrong. Let's imagine that I want to do either rejection sampling or importance sampling. And the distribution I'm interested in is a Gaussian distribution. So P is a zero mean spherical Gaussian distribution in D dimensions. And I'm going to use either rejection sampling or importance sampling using a tractable Q distribution, which is also Gaussian, which is also spherical, but with some slightly different width. So this is a toy setup, and it's a proxy for, imagine that P is not quite Gaussian. So you've got a distribution which is nearly Gaussian, but not quite, and you're going to approximate it with a distribution which is Gaussian so that you can sample from it. Now, if the original distribution isn't quite Gaussian, you might have to make this Gaussian you're fitting to it have a slightly different width in order to cover it. So if you do rejection sampling, in order to get an upper bounding envelope, it turns out that the Gaussian you use has to have a bigger width than the distribution you care about. And that bigger width means that you'll have a mismatch between the curves and you'll reject some of the samples. And the number of samples you reject decreases exponentially quickly with the dimensionality of the problem. So in 1D, if you have a slightly wider Gaussian to form your envelope, it's fine. You just have to wait a bit before you get a sample. In 100 dimensions, the algorithm basically never returns a sample. It says, oh no, I'm still drawing things that happen to be between the envelope and the curve you're interested in. Hang on a minute, I'll get there eventually. And you never actually get underneath the curve. So you could go, oh, well, rejection sampling is wasteful. I'll use importance sampling instead. And I don't have to throw away all those samples that are between the curves. I can just weight them. And importance sampling is unbiased sometimes. But it might have incredibly high variance. That just means that on average you'll get the right answer, but sometimes you'll get an answer way too big, and sometimes you'll get an answer way too small. So you can compute the variance for this setup, because everything's tractable, of the importance weights. And that's sort of a measure of how well this thing is going to work. And you do some calculus, and you get some expression. And what the expression tells you is that the variance of the estimator blows up exponentially quickly with dimensions. So again, if you're in 1 or 2 dimensions, fine. But if you have a lot of parameters, if your distributions are high dimensional, this estimator could be formally unbiased, but completely useless, because the variance is infinite or very large. As an aside, I wrote this slide in 2010, the first time I gave a machine learning summer school talk, and I wrote this slide at about 2:30 in the morning. And at that summer school, the video is still on videolectures.net, I said, this expression's probably wrong because I did the maths at 2 in the morning. You should go away and check that as an exercise. So since then, I thought I'd better go and check it myself. And so I checked this by doing Monte Carlo. I did this procedure, and I computed a load of importance weights, and I computed the variance and plotted them, and it follows this curve. So Monte Carlo is like a convenient way of checking your maths. You could look at a page of algebra many times and miss a mistake. You'd never be sure if it's right. But what are the chances that it's going to really closely agree with the experiment if you do a numerical experiment? Is pretty small, so I'm fairly confident that expression's correct. Okay, so how are we going to proceed? We're interested in large probabilistic models. We'll have high-dimensional parameter vectors theta drawn from some posterior distribution. We don't know the normalizing constant of that posterior distribution normally, and we want to be able to approximate integrals to make predictions. How are we going to draw those samples when rejection sampling will just hang and not return a sample? And if we do importance sampling, then we're probably just going to get junk answers out of our code. So here's another intuition of what's going wrong with importance sampling so we can fix our mistakes. Here I'm pretending I'm doing linear regression. So I've got a 2-dimensional parameter space. I've got a slope and an intercept of a straight line, and I'm trying to fit the red data points. And what I'm doing is I'm just drawing trend lines from my prior. So I'm not looking at the data set at all, and I'm drawing from the prior because the prior is a tractable distribution, so it's often something to sample from. So I slap down trend lines, and the first one doesn't really match the data. The next one is completely sort of at odds to the trend line. It is a terrible fit to the data. It's got importance weight 10 to the minus 8. The next one's a bit better. Its importance weight is 1/millionth. The next one is, by luck, a really good fit, and it has a much higher importance weight of 0.4. I think I've normalized these so the importance weights add up to 1. And I got that really good fit, but then I'm just drawing these panels independently. I could shuffle them. There's no order to this. So I found this good place in parameter space, but then I can go back to drawing completely junk settings again. And it's a kind of inefficient way of exploring the space. And that's just in 2D. If I had linear regression in 100 dimensions, the chances of drawing a high-dimensional hyperplane that goes through my data is so small it will basically never happen, and the algorithm will be totally broken. By the way, you should never actually do Monte Carlo for linear regression because you can do all the integrals analytically. It's just an example for the slide. Just checking there. Okay, so there's an algorithm called the Metropolis algorithm, which a bunch of you already know, here is a picture of how that would run on this slide. So if you don't know the algorithm, don't worry. We're going to see it built up. So in the algorithm, we start in the top left, and the green line is a setting of the parameters. So everything we don't know, we start with an initial guess. We just set the slope and intercept to some settings. If we had latent variables, we would set all of those to some arbitrary settings. And then we try wiggling them a little bit. So the red line is the result of randomly perturbing the mean and intercept of our current explanation of the data. And what we do is we've wiggled it here randomly, and the red line is worse than the green line. And the Metropolis algorithms decided, yeah, I think I'm going to stick with the original green line. I'm just going to ignore that thing I've just proposed because it turned out to be worse. So in the next frame, the green line's in exactly the same place, and it's tried a different wiggle of the parameters. And that wiggle turned out to be bad as well, and so it's stuck with the same parameters. In the third frame, that line has actually moved slightly, but you can't tell. So it wiggled the parameters by a tiny, tiny amount, and that turned out to be better, so it moved it, but you can't see because it was such a small move, nothing happened. So in the top frames, basically it does lots of moves that either don't do anything or are worse. And then eventually, in the second frame on the second row, it got lucky and it tried a wiggle that was a really good fit to the data. And so then it moved there. And in the next frame, because it was in a good place, most small wiggles from there will also be good settings of the parameters. So it moves to a different plausible explanation of the data. So it says, fine, I'll move there. In the next frame, it moved to a different plausible explanation of the data. It still seemed reasonably good, so it moved there. And in the final frame, its random proposal turned out to be bad, and so it's a red line, it rejected that. So rather than finding a good place and then just ignoring it, when you find a good place, you then locally explore a load of good explanations around there. So it's an alternative view of sampling. Instead of trying to draw independent samples from our posterior, we're trying to take this random walk process through our posterior that explores the space of reasonable explanations with a walk. Question?
So does the prior put a Gaussian distribution on both parameters in this example?
It probably did, yes. Another question?
There's a risk to be stuck in a local minimum with this method?
Yes, so there are all sorts of potential pitfalls with Markov chain Monte Carlo, including falling into local minima, which was the question. For the moment, let's try and understand the algorithm before we throw it under the bus. So yes, there are lots of problems. If I will hopefully have time to tell you all the ways in which you should be careful, but if I don't have time, I'll tell you now. This stuff is very easy to code up, easy to run, and has all sorts of ways of shooting yourself in the foot, so be careful. Okay, so that picture shows you what's happening in sort of model space you understand. You're seeing the trend lines move around. Those trend lines are just represented by two numbers. So what's going on in parameter space is, in the bottom right, we've got a two-dimensional parameter space, like slope and intercept, and the green line is showing that it's taking some walk through that space. And the red offshoots are saying, sometimes it considered going to a particular place in that walk, decided that that was outside the support of the posterior distribution that it's trying to explore. It's trying to explore plausible explanations of the data. And so the walk just decided not to go there, to stay where it is, and then try somewhere else. So that's sort of a cartoon of this algorithm applied to this data set. It's an old algorithm. So this is a screen grab of the original paper published after the war. So this stuff was developed as sort of part of the process of developing nuclear weapons, like all this stuff. So this is the Metropolis et al. Paper, and this method, the Metropolis method, is one of the first algorithms run on fast computing machines. There's a lot of code breaking work in the war, and there was a lot of simulation work. This is one of the earliest applications of computers. The author list is kind of interesting. So everyone calls it the Metropolis method. According to Marshall Rosenbluth, who's the third author on the paper, the only thing Metropolis did was run the computer systems that they ran the code on and gave them computer time and had zero input to the paper at all. Now, when he said that, Metropolis was dead and didn't have any chance to speak back, so we should take it with a bit of a pinch of salt. But there's this paper that Rosenbluth writes up an interview with Rosenbluth, and it sounds convincing. I kind of believe the story. So according to Rosenbluth, Edward Teller, one of the fathers of atomic weapons, had this brilliant idea that in order to understand physical systems, as it modestly describes in the paper, they have a method to calculate the properties of any substance. It's a pretty big claim. In order to understand a physical system or any substance, they could invent their own physical process, their own type of random walk that has nothing to do with the actual physics, that would be more convenient to run on a computer. So apparently that idea that you could invent your own walk process separate from the physics to explore the states that the same states of physics would explore, was down to Teller. Augusta Teller was Edward Teller's wife. Apparently she wrote an early version of the code which was thrown away and never used and didn't do anything in the paper. Marshall Rosenblatt came up with the actual algorithm, he claims. So he came up with the Metropolis algorithm, and his wife, Ariana Rosenblatt, wrote all the code and ran all the experiments. Sadly for me, we live in a different world now. I asked my partner once if she would write some code for me, and she said that she had her own research to do and showed me the way out of her office. So, but back then, actually, most computer code was written by women. And I think it's sort of interesting that it's just purely a function of the society you live in, sort of what different people end up doing. Okay, here's some of the intuition of the sort of Metropolis algorithm, where it comes from. So they were interested in physical systems. So this wasn't the system they were exploring, but here is an undirected graphical model. You could think of it as a system of magnetic spins, or you could think of it as pixels in a binary image. We've got one of these Potts models I was complaining about that say adjacent pixels like to be the same color, or adjacent magnetic spins like to point in the same direction. This is an intractable distribution in that you can evaluate the energy of any particular spin setting, but there's a normalizing constant you don't know, and there's no obvious way of sampling from this distribution. Actually, there's an amazing algorithm called coupling from the past that can sample from this distribution, but that wasn't discovered until decades later. So let's pretend that we don't know how to sample from this distribution. We can evaluate the setting of any spin setting. Now, previously, the way to sample from this system would be to simulate physics. You would simulate the system that has this energy and then look at what happens. But their idea is, let's invent our own simplified process that is easy to implement on a computer in discrete time that will also end up exploring this distribution. They want to make local moves. So just as I was moving around these regression surfaces, if you've got a whole load of variables, a way of making a local move is don't try changing all of them. So just try tweaking a few of them. So here is a distribution Q, which instead of just sampling a random image, samples an image conditioned on the one that we currently have in mind. So the new image x prime is going to be very close to the old image x. And so here are 3 different images which are all slight tweaks on the original one. So the Metropolis method has this distribution Q which mutates the current position. And what it aims to do is construct a Markov chain. So that's a type of process where the current state only depends on the previous state and you don't care how you got there. So you get an image, you mutate it, and then to get the next image, you just mutate the current image and you don't care about how you got to the current image. And what their goal was to construct a Markov chain, one where you sample the image at the current time based only on the previous image, in such a way that if they ran this Markov chain for a long time and looked at where they ended up, that final image would be roughly drawn from the distribution they were interested in. So they're wanting a walk process that will walk through plausible images from their system, or if you're using it for Bayesian inference, walk through plausible settings of your parameters so that when you look at the final setting, you have an image that could be produced by your physical system, or you have parameters that could be drawn from the posterior given your data. And so now you've got an interesting problem. When I learned about Markov chains in maths classes, the questions usually said, here's the definition of a Markov chain, compute its stationary distribution, and you did stuff with eigenvectors and stuff. Here the problem is the other way around. We know what stationary distribution we want, construct a Markov chain that gives us that stationary distribution. And that's an ill-posed problem. There are lots of different Markov chains that you could pick, so you want to pick one that is easy to implement, that you can check definitely does have the right stationary distribution, and hopefully one that zooms around your space kind of quickly rather than taking 5 million steps to sort of get from one image to another. Okay, so there are a couple of rules that you can follow to try and construct a Markov chain that satisfies this property that you draw samples from a distribution you want, P. So in all these slides, P is the distribution we're interested in. Q is usually some arbitrary distribution that's convenient to use. So this equation is the sort of most important condition that a Markov chain algorithm should satisfy. And what it says is, if you draw an image x from the distribution you're interested in, P, if you had an oracle that could magically sample a whole state from the correct distribution, and then you take one step of your Markov chain process, so there's a transition probability distribution that takes you from this image to a new image x prime, then that defines a process, the process of generating something from the right distribution and taking one step. And on the right-hand side, we've got the probability of where you end up in that process. So the distribution of where you end up after taking one step of your process. And there's a basic self-consistency property that says that distribution on the right should be P. It should be the distribution you care about. So you don't it's a way of generating a sample. You start off with a sample and then you mutate it. It's like making yogurt. If you want yogurt, you need to start with yogurt and you make more yogurt. If you want a sample, you need to start with a sample and then you take a step and you get another sample. Those two samples are correlated. X and x prime are related to each other. But if you threw away the original place you started x, x prime is just as good a sample as the original. Okay. There's a second property that the algorithms need to use, and you'll see it described in various ways in different papers, and I'm not going to be very formal about it. But the word ergodic is often used, and the word ergodic can mean different things in different papers. But one of the things that it can mean is that it's possible to sort of get around your whole sample space. So if you initialize your Markov chain in some way, like you put all your parameters at the origin, or you draw a sample from your prior, you need to be able to get away from that initialization, which is often arbitrary, in order to draw a sample from the distribution you care about. So I've had a few iterations at this, and this diagram is my current attempt to explain ergodicity, and I'm sure it's not the last attempt. This is my cartoon of a high-dimensional distribution. So we're often navigating very complicated spaces. The reason we're doing Markov chain Monte Carlo is because we're trying to draw from a distribution which is hard to characterize. And this cartoon is saying there could be lots of spiky arms. So let's say we have a large neural network model with 100,000 parameters. There could be some branch of the parameter space that sort of fits the data well, and then you can move all the parameters around and find a completely different solution in parameter space that also fits the data pretty well, and that's in some different arm of parameter space, and that's also perfectly plausible. And so if you have a large model, you've got to there's lots of spindly places you could go down and you could potentially explore. Our Markov chain algorithm will start somewhere in that parameter space, somewhere arbitrary, and it will take some walk through the space, and it will end up somewhere after some number of steps. What we want is to run the process for long enough that it could get anywhere in this space. If we only ran it for a short time, we'd be stuck to be close to where we started, and we wouldn't be able to claim that our final place was a good sample from the distribution. We want to run it for long enough that it could have potentially gone down any of these arms and end up anywhere in the support of the distribution. What we don't need is to explore every single arm. So in an interesting problem, you are never going to run your Markov chain for long enough to visit every mode of the distribution or every arm of the distribution. And that doesn't mean the approach is invalid. The process just needs to have some probability that on another run it could have done that. If I started here again and ran my Markov chain code with a different random seed, I'll end up somewhere else, and maybe I could end up down here. If my process wasn't run for long enough to end up down here, or if my space was disconnected and had isolated modes, so it wasn't possible to get to some places, then I'd be in trouble. So the two things we're looking for in a Markov chain are basic self-consistency. If you start out with a good sample, the next thing is a good sample too, and the ability to walk anywhere in the space. And if you combine those two properties, that's enough to prove a whole load of results that say that this procedure is sort of basically sound. Okay, so the review is we'll have some complicated distribution that we only know up to a constant. We want to draw samples from it, and the way we do that is we initialize our parameters or our big state vector or our image or whatever it is in some arbitrary place, we run some walk process that will explore around the space, and then as long as our transition process satisfies a couple of properties, we can use all of the points that it visits as samples from our distribution. And we can throw those samples into some basic Monte Carlo estimator to approximate integrals. All of those samples are correlated with each other. If you look at the places that it visits at adjacent points in time, they're strongly dependent. But it turns out that doesn't upset the simple Monte Carlo estimator. You can still approximate integrals using all of those samples. You don't need to thin them out or anything like that. If you want to compute error bars on your approximation and say how wrong you might be, that's tricky. But the estimator itself, you can use all of the steps of the chain. OK, so I still haven't actually said how we do it. We want a transition operator that satisfies these properties, but how on earth do you come up with such a thing? And I've turned this around. I always used to explain the Metropolis algorithm first, but I've decided that Gibbs sampling is actually easier to explain. So Gibbs sampling is an algorithm where you take each variable in turn and you sample from its conditional distribution given all the other variables. So if you've got one of these image models or models of spins, I go to one of the variables at random, I throw away its current setting, I forget whether that was a black or a white spin, and I sample, given its neighbors, I say, what's the conditional distribution? This one doesn't care because it's got 2 black neighbors or 2 white neighbors, so it will just flip a coin and it will set itself to be black or white with probability a half-half. If I were to update this neighbor, it would be strongly biased towards being black because all of its neighbors are black. So that's the discrete setting. The discrete version is really easy to implement because you're updating one discrete variable and you just work out the probabilities. You can explicitly normalize them and do the sampling on a stick algorithm. The continuous version might be harder to implement. In the continuous space, you're doing axis-aligned updates. So this blue curve shows the random walk, and you either move horizontally or vertically. You clamp all but one of the variables, and you have a one-dimensional PDF that you have to work out how to sample from. And you could do that, say, using rejection sampling if it isn't of a standard form. Okay. And you have to be slightly careful. The transition operator in a real space is all but one of the variables stay the same, and there's a delta function there, and the other variable is sampled from its conditional distribution. And I told you to worry about delta functions. If all your updates are axis-aligned, all the maths comes out in the wash, and you don't have to worry about that. If you're picking which directions you're going to sample along cleverly somehow, you really have to worry about this delta function. If you find a paper called Adaptive Direction Sampling, it will explain in excruciating detail ways in which you can screw up and how to fix it. Okay, so why is Gibbs sampling valid? It seems like a natural thing to do. You just sort of have an explanation and you perturb one thing at a time. I think to prove that it's correct is actually pretty easy. And so I think of it using the following story. We've got a joint distribution, P of x. X here is a big vector over 100 spins or 100 parameters. And we can factor, using the product rule, that joint distribution into the probability of one variable and the probability of all the other variables. So we could first sample all but one of the variables, and then we could sample the final variable I given those. And that would be a valid way to sample from this distribution. Okay. So how do we implement that? How do I implement sampling all but one of the variables? Well, an easy way to sample from a subset of variables is to sample all the variables and throw away the ones you don't want. So I could sample all but one of the variables by sampling all the variables and throwing one of them away. Okay, so I'm building up a convoluted idea here. I'm going to draw a sample by sampling the whole vector, throwing one of the elements away. That gives me a sample of all but one of them, and then I'm going to sample the final one again. Okay. And that process, I think, is obviously valid. It's the correct way of sampling from this distribution. And so what it's telling us is that if you take one of the variables out and you resample it, that will take a sample and it will take you to a new sample. It satisfies the self-consistency property. And this view of the correctness of Gibbs sampling is useful for understanding the versions that are used for non-parametric models. So I think it's more useful than what's often in the textbooks, which describes it as a special case of Metropolis. Okay. I'd be interested to see whether people followed that. Tell me in the break. All right. Where do other Markov chain Monte Carlo methods come from? So Gibbs sampling is just one choice. It's one particular Markov chain where you update one variable at a time. Where do other methods come from, and how do you check they're valid? So let's first imagine that someone gave us a Markov chain, and it was a valid Markov chain. So they gave us a transition operator T that will take you from a state to a new state. What I'm going to do is take that and create a new transition operator, which I'm going to call the reverse operator. And I'm going to define that as proportional to the transition operator they gave me multiplied by the distribution I care about. So I'm defining an operator that will take you from x prime to x, and I'm defining it as being proportional to a transition operator that would take you from x to x prime multiplied by the probability of x. So I'm free to do that. I'm free to invent a probability distribution that's proportional to some positive numbers, and there's nothing, I can always do that. The thing on the bottom is just the sum of the top over all settings of x. So it's just the normalizing constant that makes this thing a distribution over x. That normalizing constant turns out to be simple because we've been told that T is a transition operator, so we substitute in the properties that transition operators satisfy, which gives us P of x prime here. You'll notice this thing looks quite a lot like Bayes' rule. I'm sort of inferring where I came from given a new state, given that I know that this transition operator was used. So you could think of this reverse operator as infer where someone came from using a transition operator and then sample from that distribution. So this thing must exist given any Markov chain Monte Carlo algorithm. For any Markov chain Monte Carlo algorithm you see in the literature, this thing exists. It might not be particularly tractable, but it will exist. So because it always exists, there's a necessary condition that this equation must hold. If I multiply both sides by P of x prime, it gives me this more symmetric looking thing. So for any algorithm that has a way of going from x to x prime, there must exist another algorithm that could take you back from x prime to x that satisfies this balance condition. A lot of you will have probably seen this version where r is equal to t, and then this equation is called detail balance. So the equation I've put up is necessary. It is always true for any Markov chain Monte Carlo algorithm. Detail balance is not necessary. It's not necessary for r and t to be the same thing, but it commonly is. So what this tells you is that Markov chain Monte Carlo isn't like optimization. Optimization says you're going to find like the best point in your space, and you really don't care about where you came from, and everywhere collapses into one point, and then you're going to forget where you came from because everything goes into this one point. You don't know where you came from. The existence of a reverse process tells you that you can't sort of greedily go into a mode. You're going to have to do something that you could imagine running in reverse. So I have a cartoon of that. On the left-hand side, we've run a Markov chain process. It's some random walk through our space. On the right-hand side is the same walk going backwards, and we've got to believe that that walk going backwards could exist. So if walks always crush into one place, if you look at them time reversed, it sort of wouldn't look sensible and you wouldn't believe it exists. So Markov chain Monte Carlo algorithms are fundamentally different from optimizers, and you can't always use the same intuitions. This balance condition is necessary. It's also sufficient to prove the property we want. So if you sum both sides of it over x, you return the invariant condition that you have to satisfy. So a way to prove that a Markov chain is valid is you come up with some description of how you would reverse it, and then you're done. So the Metropolis-Hastings algorithm does satisfy this balance condition. This was the algorithm where you're at some point in your parameter space x. To get to a new place x prime, you have to propose that using your arbitrary mutation process. And you also have to accept the move. And the probability that you accept this new position x prime is some standard expression that you use for all models. And that expression involves how good is the new place compared to the old place, and how often do you propose going to the new place compared to the old place. So if the new place is good, you tend to go there. If you tend to propose going to this particular place a lot, then you'll get penalized for that and you won't go there. So if you derive Q from an optimizer and you always propose going to the same place, then this term will kill you because your probability of going back will be 0. So for those who haven't seen it before, I think it would take you a while to work through the details. There's some details in the slides that describe the algorithm and give the proof. I won't go through that. There's also complete code for the method, which I'm also not going to go through line by line. But the thing to notice is that this is code that will take a function handle for a that evaluates a distribution that you care about up to a constant, and it will give you a Markov chain. So the code is incredibly short and doesn't contain any complicated maths at all. So in principle, at least, although you can get trapped in local optima and there are loads of other things to be careful about, these things are very easy to run. So let's see how it behaves. Here I'm using the code on the previous slide. This is the code that produces these plots. And I am sampling from a one-dimensional Gaussian distribution. So I'm pretending that that's an intractable distribution that I need to use Markov chain Monte Carlo to explore. So the x-axis here is time or iteration number of the algorithm. And it's just showing where this Markov chain visited over time. So the Metropolis method has the distribution it's trying to explore, P, which is here as a unit Gaussian. And it also has this distribution in Q that says how do you mutate the current state. So in the top plot, Q is a Gaussian with standard deviation 0.1. So it's taking really small steps compared to the width of the distribution. And that means that if you start out in a good place, if you move a tiny distance, that's also likely to be a good point in your state space, and it's likely to be accepted. And so 99.8% of the moves are accepted. And unlike in rejection sampling, this is a terrible thing to happen. So this is an algorithm where you really don't want to have every step accepted. And the reason is that this plot has almost nothing to do with the distribution I'm interested in. This plot is almost exactly a Gaussian diffusion with step size 0.1, because apart from the 0.2% of places where it did something different, that's exactly what it is. So the only way this algorithm sees the distribution you're interested in is through the fact that you try to step places and you get rejections that say, no, that's wrong. If this message you get is, yeah, that's fine, then you're never actually getting any information that says, that differentiates between that's a good place and that's a bad place. In the second plot, we've taken bigger steps comparable to the size of the support. We have many fewer acceptances. And now if you were to plot a histogram of these where the Markov chain is visited, it will look much more like a unit bell curve than a histogram of the top states. So increasing the step size was a good idea. We move further. We're not just taking a small, tiny diffusion close to where we initialized. If we increase the step size again, then bad things happen the other way. Now almost all of our points are rejected because almost all of our proposals are just places which are not plausible given a unit Gaussian. So we propose going out to +20, and it says, no, that has really low probability, don't go there. Except occasionally we get lucky and happen to make a small step, and so you can see the few places that it accepted on the plot. So these algorithms are a pain because they have step size parameters and you have to set them, and so you have to go and do initial experiments to decide how to set them until you decide that you should use slice sampling instead, which I won't have time to explain, but there's versions of this algorithm that will set the step size for you. Yeah?
Can I adapt the step size on the fly?
Yeah.
Does it invalidate?
Sorry to the people on the video that just heard me sneezing. The question was, can I adapt these step sizes on the fly? There's a very short answer, which is no. If you decide to think, oh, I've got my acceptance rate is really low, I'm going to take smaller steps, and then you start accepting a lot and you make bigger steps, and you're not careful, you can easily bias what's going on. A cartoon of that is if you've got a state space where you've got a huge cavern and a narrow part to it, then you're walking around here with tiny steps, and you go, I'm accepting all the time, so let's make big steps. And you walk around the space like this. And then you get in here and you start rejecting all the time. And you go, oh, I'm rejecting all the time, so let's make small steps. And then you're going to spend way, way longer in here than in here. So it's incredibly easy in an interesting hierarchical model where, depending on settings of hyperparameters, volumes of other parameters change, to get incredibly large biases that will change your predictions in ways you can't anticipate if you adapt the step sizes naively. That said, there's a whole literature on how to do it more carefully. So the message is, don't adapt step sizes by just writing some hack yourself to do it. If you want to do that, you need to read some papers or think very carefully, and probably read some papers because a lot of thought's already gone into it. Yeah?
Is it necessarily better to have a higher acceptance rates because is it in some way related to variance of the estimators?
So the question is it bad to have small step sizes? Is it related to the variance of the estimators? So for simple setups like this, people can derive what's the optimal step size, or another way of putting it is, what's the optimal rejection rate to have or acceptance rate to have so that your estimator will have small variance. So for a wide variety of setups and for this simple Metropolis algorithm, the optimal acceptance rate to go for is, I think, 0.234. It's about a quarter, and that's been derived theoretically. I think don't spend ages optimizing to get exactly 0.234. I think the only reason it's equated to 3 significant figures is because it's this nice number. But yes, there are theoretical reasons to have a high acceptance rate. There's an argument in David Mackay's book, which is intuitive but not quite right, which says that you're getting information from the distribution through the acceptances and rejections. And if you look at a binary outcome, the most informative probability for a binary outcome to have is to get 1 bit of information, which you get when that outcome has probability 1/2. So if you're uncertain about what the oracle is going to tell you when you say, am I allowed to do this move, then you're getting the most information you can, and so you intuitively want acceptance rates of around 1/2. If the acceptance rate is probability 0.99, why are you even asking the oracle? Because you kind of know what the answer is going to be already. So that's sort of an intuition, but this other theory says that it's not quite the right answer. But if you aimed for an acceptance rate of 0.5, that would be fine too. It would work fine. These methods are valid no matter what you set the step size to. It's just for some step sizes, you're going to have to wait longer to get reasonable answers than for others. Yeah, there's a question.
What about multimodal distributions?
Yeah, so a lot of these cartoons sort of describe that you've got one distribution and that there's one step size. If you've got a multimodal distribution in high dimensions, then the answer might be you're stuffed. Like, it might be unreasonable to expect some dumb algorithm perturbing your state to ever find another mode in high dimensions. How will it possibly teleport over there? There are a bunch of sort of meta heuristics that sort of attempt to solve that problem, annealing methods. Maybe you've got knowledge of your problem that would help you do that, but the answer in general is there are problems that are kind of impossible to solve. It also depends on whether you care about the modes. So let's say I've got a data set with data that looks like that, and I'm going to fit a clustering model, and I'm going to fit a mixture of 2 Gaussians. And let's say I know the widths of the Gaussians, so I have 2 parameters. One is mean 1, and one is mean 2. Then my posterior distribution says, well, I could have mean 1 being around, being small, and I could have mean 2 being bigger. So I could have some posterior distribution. This is a contour plot of the density saying the means could be around here. But these labels 1 and 2 are arbitrary. An equally good description would be if that was mean 2 and that was mean 1, then it would still fit the data. So you'll have another mode to the distribution down here. So now we've got this distribution and it's got two modes and they're isolated and you can't get there with axis-aligned moves, so Gibbs sampling will never move you between the modes. But if you look at the predictions that this mode will make and the predictions that that mode will make, they're exactly the same. So you might not care that you only ever see one of them. If you're doing, for those that know about this, if you're doing model comparison and computing marginal likelihoods, then yes, you're in trouble if you don't find all the modes. But this is a rabbit hole that I've gone down too far already. So let me get back to basics. If we have one mode, then we could sort of try and understand a bit more about the effect of these step sizes, or in general, what's the problems that Markov chain Monte Carlo faces. So the variables that we're interested in are often dependent or correlated, because if they weren't, then we'd have an easy problem. We wouldn't need Markov chain Monte Carlo. So we're sampling multi-dimensional distributions, and the ellipse is showing a contour of a probability. So the cartoon is we're wanting to explore the space inside this ellipse. If we make dumb generic proposals, so we're at a current point and we make a small perturbation Q, say in a sphere around where we currently are, or we make axis-aligned updates that only move locally, horizontally, or vertically, then we're limited to make steps that are pretty small, sort of limited by the shortest width of the distribution that we're wanting to sample from. If we make really large proposals that are much wider than I've drawn, then most of them will get rejected. And this cartoon is especially true in high dimensions. So actually in 2 dimensions, the optimal width would be big because you'd reject a lot, but every so often you'd hit the end of the distribution and you make a big step. In high dimensions, if you perturb with a wide distribution, one of your dimensions will be wrong and you'll reject no matter what. So you have to take small steps to stay on the manifold of high probability. So if you take small steps of width sigma, and you need to move distance L to get from one end of the distribution to the other, then it's going to take ballpark L over sigma squared iterations to do that by a random walk-like process that moves it around. So if you make the step size 2 times smaller than you could have done, then you're going to multiply the number of iterations you need to sort of get around the distribution by a factor of 4. So setting these step size parameters can be a pretty sensitive, hairy thing to do, which is again why I'd recommend reading the literature on things like slice sampling that avoid you having to set them and avoid you shooting yourself in the foot by getting them wrong. Okay. One other thing to say about Monte Carlo is that it can be a bit scary. You have to make choices. So you have to set step sizes, and maybe there are a few different step sizes you might want to use, because maybe sometimes you want a big step size and sometimes you want a small step size. And it might be that you go to a summer school and you hear about Hamiltonian Monte Carlo, and you hear about slice sampling, and you hear about some fancy tempered transitions thing where you read papers on all these different methods, and you don't know which one to use. And the wonderful thing about MCMC is that you can just time slice doing all of them. So you can take one step using a small step size, and then you can take another step using a big step size, and then you can take the next step using Hamiltonian Monte Carlo, an algorithm you'll hear about tomorrow. You can take the next step using some other transition operator, and you can just do them one after the other. And that whole process is itself a valid meta-Markov chain Monte Carlo method that does the right thing. And it might be that some of those individual methods can do really well in some part of your space, but by themselves aren't ergodic. They're not able to explore the whole space. But that's fine. If they're combined with other operators that can deal with other bits of the space, then your overall method will work well. So there are other approximate inference algorithms where if you try and sort of combine them, the combination will work as well as the worst thing in your mix. Whereas when you combine transition operators in Markov chain Monte Carlo, you often end up doing better than any of the individual methods individually. So it's something that makes these things a bit easier to use and can make you worry less. You can just try a bunch of stuff and put it all in the mix. If you combine 3 different operators and only one of them really does anything and the other 2 are junk, all you've done is multiply your computer time by a factor of 3. And that's not great, but it is better than your whole method not working at all. Okay, so the big picture of Monte Carlo is that we're wanting to solve sums and integrals, and that often involve high-dimensional distributions that we can't sample from directly. And MCMC is one of the sensible ways to sort of get going quickly to get some idea of what those integrals are. So you perturb a current state, you assume you know all of the settings of everything in your model temporarily. You look at how good that explanation of your data is, you move it a bit, and you see whether that's better or worse, and you perturb through the state space of explanations of your data, and hopefully you'll explore plausible explanations of your data. So let me show you a cartoon of what samples might look like in a problem, and what can happen. So this was a quick thing I hacked together before Christmas a couple of years ago. It was a challenge on Kaggle, which I thought looked like low-hanging fruit. And I didn't win, I came second, but the guy who won did almost exactly the same thing as me. So I think it was sort of a strong signal that it was the right way of solving the problem. It was a problem to understand dark matter, which I won't explain in detail, but if we are here at the blue place and we're looking at a galaxy far away and there's a load of dark matter in between us and the galaxy, the dark matter acts as a lens which distorts the light that's coming in. In the extreme case, you end up seeing two galaxies that look like mirror images of each other, suspiciously identical apart from their mirror images, and they're actually two views of the same galaxy. This challenge was about a weaker lensing effect where you just get slight distortions. So if you started out with circular galaxies, that's the panel on the left, then dark matter would distort the light so that they would all look elliptical and they would form concentric circles around the dark matter. Unfortunately, galaxies aren't all circular. They start out looking elliptical. So you start out, the truth is you have a load of jumbled ellipses. You put a dark matter halo in the middle, and there's a bias towards them forming concentric circles, but it's all very messy and noisy. So here's an example challenge from that data set. It showed you this synthetic view of galaxies, which are represented as points and ellipticities. And the question was, where is the dark matter halo in this field? So any guesses? Can we see where the dark matter halo is? Is it up in the top left? Is it around here, maybe? So in this image, it's completely obvious where the dark matter halo is. There is noise in this process, but there's a whacking amount of evidence that we can tell that it's sort of more or less precisely here. And you can write down a probabilistic model that says, here is my prior over ellipticities of the galaxies. This is the way dark matter bends light. This is how it will change the distribution over ellipticities of the galaxies. But I don't know how big the dark matter halo is. I don't know how massive it is. I don't know where it is. It might have some weird distribution within it that changes what happens very close to it. So you might end up describing a dark matter halo with 5 or 6 numbers, none of which you know. So 2 of the numbers are where is it, which is there, and you have a bunch of other numbers describing how strongly it will bend all the light around it. Okay, so that's the true position. Here's another image. And we were told here that there were 3 dark matter halos in the image. And the question is, where are they? And now it's a bit harder. And I looked at this for an incredibly long time and decided that I didn't really know. What's fun is you can show this to cosmologists, and they will do the thing that humans are very good at and spot spurious patterns and will say very confidently, oh, there's one there and you're wrong, or there's one there and you're wrong. And it turned out that that's the truth. That's where they actually are. Some of them are more massive than others. So what I'm not plotting is the mass of them. And if they're a very small dark matter halo, then they hardly have any effect. And so they are hard to spot. So I built a model of that, which I won't have time to get into. And the bottom line is that nothing here is going to be that amenable to standard approximate inference. Nothing looks Gaussian. Writing down a model and doing Markov chain Monte Carlo is the plausible way forward. So on the easy problem, it's easy, and whatever you do would work. So you start out with some guess as to where the dark matter halo might be. I drew that uniformly from the whole patch of sky. I also drew some guess of how massive it is and all its other properties. So I have a vector of like 5 numbers describing a dark matter halo. I then tweak them a bit and say, is that good or bad? I then tweak them a bit, and I explore the space of possible dark matter halos. And I tend to take the steps that it will explain the data better, and I sometimes take steps that explain the data a little bit less well, but that are still plausible. So I'm running slide sampling here. It's a slight tweak on the Metropolis method I showed you, and it very quickly just zooms into here and then takes very small steps saying, yep, I'm pretty sure that it's around here. So it takes this walk through plausible explanations, but all of those explanations are in a very small region of the space. If you run that on a situation where you're less certain, it's more complicated. So there's a red dot here, which is one of the dark matter halos. I've just plonked it down at random. There's a blue dot up there, which is another one, and there's a green dot here, which is the third one. I've just plonked it down at random. So my Markov chain state here is about 15 numbers. There's 6 numbers giving the positions of those dots, and there's other numbers describing their masses and cutoff radii and things. So I'm now taking a Markov chain process through that 15-dimensional space, and I'm just plotting 6 of those dimensions for you. I then perturb that whole 15-dimensional vector, and I can plot where those 6 numbers, which I'm actually visualizing, have hopped to, so they move somewhere else. I perturb the whole vector again, and I move it, and they go somewhere else. And I take this walk, and you run this for quite a long time, and stuff happens, and then 10,000 iterations later, you look at all the places you visited. So the colors here kind of don't mean anything, just as the labels here didn't necessarily mean anything. But I'm just keeping track of where these things went. I'm not running 3 separate Markov chains. I'm running one Markov chain on a 15-dimensional space. And I've thrown away time here, so it's hard to see exactly what's going on. But you can see that the colors are arbitrary because there's probably a dark matter halo around here, and there's the crosses, so the true position. So it's seeing that there's probably one near that halo, and it's seeing that there's probably one near there. And it just happens that I plotted the red dots last, so they're all on top. But underneath those, there's a load of blue dots, and there's a load of green dots. So all of the labels did swap around when I did the sampling process. If you've got a really noisy problem, then mixing is much easier. If you've got a lot of tight constraints, then inference is actually harder. And what you can tell is that we're pretty sure that there's halos around there and there, but there could be one almost anywhere else if it has really small mass, because if you have a halo with small mass, then it could be anywhere because you can't really see it. If I throw away the colors, and I've now represented the mass by the darkness of the dots, so it thinks there are massive halos around here, and if there are halos in other places, they're relatively much lighter. So the question, if you do something like this, is how do you report the results? It's all well and good. I've done my inference, I wrote down my model, and now I beautifully represented my uncertainty because I've said I can give you 10,000 different explanations of this data set that are all sort of semi-reasonable that you wouldn't be able to say are definitely wrong. But that's not a good thing to put in a paper. Like, you can't say, oh, we did our inference, and in Appendix A, you can see the 10,000 different explanations of the data that all might be OK. You need some sort of compact summary. So one thing you might think is, well, let's average the samples. And that's going to be a disaster, because the red chain moved almost everywhere in the plot. So the average position of the red halo will be sort of there, not near any of the actual halos. The average position of the blue halo will be also there because the colors are arbitrary, and the blue part of the chain will have gone to all the same places. So the mean sample position is meaningless and wouldn't be a good summary. A lot of people would think, oh, I could propose the most probable sample. And I'll tell you in a minute why that's a terrible idea. But also, this is the wrong algorithm to be doing that. If your whole goal was to come up with the most probable explanation of the data, then use an optimizer, because Monte Carlo methods are terrible optimizers because they're not optimizers. So why run this Markov chain just to pick out the most probable point when you could have probably got there a lot quicker using another method? You might have all sorts of ideas about, oh, I can see clusters here, and maybe I should run some sort of clustering algorithm on the points. But if you think about it for a bit and sort of try and think how you would do that and meaningfully report where you think the 3 things are, it's kind of tricky. It's not obvious how to summarize the results in a clustering. Okay, my actual objective was to win some internet points by trying to win the Kaggle competition, which I failed because I came second. But the objective there was very nicely quantified. They said, we're going to measure you by this metric. And so what I wanted to do was minimize this loss function. And it was this crazy thing that I'm not going to explain in detail. But it had 2 terms that said your root mean square error should be good, so your guesses should be as close as possible to the truth. And there was this funky term G that they added to it that was trying to discourage you from certain sorts of bias. So it didn't want you, for example, to shrink the dark matter halos closer to each other than they actually were systematically. A lot of machine learning methods benefit from shrinkage, and they shrink things towards common points, and they're explicitly trying to stop you from doing that. And here's why. Here's a version of the problem in 1D. So the sky is now the x-axis, it's a one-dimensional sky, and we're observing sheared galaxies where the shear is measured on the y-axis. So here, the truth is there are two halos, and they're at 0 and 1. And if you fit a probabilistic model to this thing that's got two peaks in it, and you try and locate where are the sources of shearing that are causing these big peaks, then the red lines aren't the truth here. I'm drawing the maximum likelihood solution. So the most probable explanation of the data that you'd get with an optimizer is like bang on the truth. This is an easy problem, and you get the right answer. No need to do Monte Carlo. If you did do Monte Carlo, all your samples would be on top of those red lines. If you've got less data, though, you're not going to recover the truth by doing maximum likelihood. So given this sparser data set, those red lines are showing the maximum likelihood solutions. The truth is still at 0 and 1. So here, the maximum likelihood solution is further apart than the truth. If you draw a different data set, then here the maximum likelihood solution happens to be closer together than the truth. So sometimes you'll get an answer that's too big, sometimes too small. That's to be expected because you've got limited data. The problem is that if you look at many synthetic data sets and you do maximum likelihood many times, then the average separation of the maximum likelihood solution is closer than the truth by about 4%. So if you don't deal with uncertainty, you just say, I'm going to come up with the most probable explanation every time, then you have a systematic bias. You say, when I estimate the position of dark matter halos, I put them closer together than they actually are. So, like, on average, I do that. And that's a disaster for physics because that's a small effect, but one that you could measure. And you'd go away and you would write a paper that dark matter attracts together like more than conventional matter, and you would start like telling the theorists to come up with new physics. And it's an entirely spurious effect of the statistics. So that's why when they invented their loss function, they were trying to stop you coming up with these biases. So here's another way of putting it. I was fitting a particular graphical model. I had positions in the sky where there were galaxies, and at those positions I saw some ellipticities. There were some halos that described how all of those ellipticities would be biased from their normal distribution. And I can draw a whole load of samples from these halos, and it's not an easy to summarize thing. I shouldn't maximize it because that will lead me to trouble, and I can't just give you a list of a huge number of possibilities. Why do they want to do this inference problem? Well, it's because they have some theories about how these halos are going to behave. So they actually have a bigger model in mind where they have multiple skies, and they have some parameters from their physical model that says how these halos are going to be distributed. And their final goal isn't to locate the dark matter at all. They don't care where the dark matter is. Their goal is to validate or disprove their physical theories that describe how these things are distributed. And so the thing to estimate is the much simpler quantity, the 1 or 2 parameters in their physical model that describe the distribution over the halos. And that should be the target of the inference. So the target shouldn't be to come up with some guess of where the halos is. If you look at the posterior, we clearly don't know where they are, so we shouldn't pretend we do. We should just try and use all of that uncertainty, integrate it out, and estimate the things that we actually want to publish a paper about, and say this parameter theta takes on this value plus or minus this error bar. Okay. You will have far more questions than I have time to answer about how you actually go about these things. Some of you are acutely aware that there are all sorts of problems that you could run into. So you might have multiple modes, and we know that if we initialize arbitrarily, a Markov chain will fall into one of them and ignore the other. And what do we do about that? And the answer is, yes, that's difficult. Do we need to try and throw away this arbitrary initial Benin period? One answer is probably. Another answer is maybe you can think harder about how to initialize. And a lot of problems, there's ways of coming up with plausible points to start with, although running an optimizer can be a dangerous one. How do you know whether you run for long enough? Are there any guarantees? I'm afraid I'm not going to have time to answer all these questions. Well, if you have specific versions of them, I might be able to say something good. So I've put in the slides a couple of links to some papers. So this is now an incredibly old paper, 1992, Practical Markov Chain Monte Carlo. A lot of the advice still equally applies. You know, we're still fitting a load of the same models. This is a solid paper that I think has got a good discussion of some of the obvious issues, like the questions will come up within the first 10 minutes of trying to run these things. I'd have a look at that paper. There's some standard diagnostic software, like there's a package that comes with R that can give you some useful plots. I'd look at that. I'm afraid I don't have time to go into the details of what it does. But none of these papers or packages are going to give you a strong guarantee that you haven't thrown away some mode. Like, unless you've got some special insight into your problem, proving that you haven't thrown away some important mode is not going to be easy. What I want to spend 5 or 10 minutes on, instead of talking about all the standard stuff you can read in papers, is tell you where I've actually had problems and things that really make a massive difference at a low-hanging fruit. And that's sort of checking that you haven't just done something obviously stupid, that like not implementing the method that you wrote down in the algorithm box in the paper, which is surprisingly easy to do. So what you should do before publishing a paper is a load of consistency checks that sort of show that what you're doing isn't obviously wrong. And it might be obviously wrong because the Markov chain isn't going to mix properly, and it could be obviously wrong because your code is just wrong. So you should check, when you have a large data set, often you'll get some result out from an inference algorithm, even if your code's totally wrong. So a good check isn't get your big complicated data set, run your method, and have a look at the results, because you have a bias of what you want to see, and if you see what you wanted to see, then you'll just go with it, regardless of whether it was the right answer. So if you've got tiny versions of your problem where by brute force you can work out the right answer, and by the right answer I mean the whole posterior distribution, then you can like really hammer your code against a small example and check that it works at least there. You can also run your code on synthetic data before you touch the real data. There was a good question about this yesterday. So before I ran my code on the data from the solar system, I generated lots of synthetic solar systems and checked that the right answer was within my error bars sort of 95% of the time. And if your code doesn't work on synthetic data that's actually drawn from your model, then there's no way it's going to work on real messy data, which is going to have some problems with it. So that's all sort of checks that the method can sort of possibly work. There's a paper called Getting It Right, which I highly recommend the general idea of the paper to check that your code is correct. And some similar checks you can do with posterior model checking, which is in the Bayesian data analysis book and some of Andrew Gellman's papers. So the Getting It Right method has literally saved me from publishing embarrassing mistakes. I have made mistakes in my code, which this has caught. And it works as follows. You have a parametric model. It's got some parameters theta, and it generates some data y. You might also have some hidden variables. Just shovel those into theta for the purposes of this explanation. So you just spent a week writing Markov chain Monte Carlo code that will update the parameters given the data set. So you've observed y, you start with a random guess of theta, and you've got code that will now move theta around and hopefully end up moving it around good settings of theta. The idea here is you should spend another half an hour writing some new code that will sample data sets from the parameters. So code up the forwards generative model. That's usually simpler than trying to do the reverse process. In fact, you should probably do that first, because you can look at samples from the model, and if there's obviously wrong things with them that a priori you know are wrong, then you can fix up your prior and come up with a better prior. So it's good practice to code up the forward generative process anyway. Okay, so now we've got two Markov chain transition operators. One moves theta around, and one moves y around. And both of those Markov chain transition operators leave the joint probability of everything invariant. So the probability of everything is proportional to p of theta given y. So your Markov chain Monte Carlo code leaves the probability of everything invariant. and the data generating process is just part of the joint distribution running forwards. So what you can do is alternate these two bits of code. First of all, start with some arbitrary parameters and generate some synthetic data using those parameters. Then clamp your synthetic data and move the parameters away from the parameters that actually generated that data to some other parameters that could have generated it that are sort of equally plausible if you didn't know. After you've moved the parameters, throw away the data set and generate a new synthetic data set that could also have been generated from those parameters and repeat. So you go back and forth updating theta and y. So you do that, and you know now you've sampled from your joint prior over everything. You might have a parameter theta1, which was a priori Gaussian normal 0, 1. Right? So you know what the distribution over one of the parameters should be. A common thing that's happened to me is I write down my complicated model. It has a parameter which is a priori Gaussian. I run this procedure, and I plot a histogram of the theta 1s that the Markov chain runs, and I get this distribution, or something that's obviously not the same. Having a chunk cut out of the distribution is a common pathology, actually. When you make a coding mistake, it often vetoes some part of the parameter space, and so you see weird cuts taken out of your distribution. If all of these checks you do pass, you don't know for sure your code is correct, but I found it very hard to make mistakes that will not upset this check. Like I've tried going into code and making subtle mistakes, and this check sort of immediately upsets the Markov chain and will manifest itself in some obvious way when you look at your histograms over your prior quantities. Okay. I'm going to finish with one final warning and then give you some time for questions. So I have here a real valued variable, and it varies between 0 and 10. And I'm going to construct a Markov chain for it. And Iain Murray told me that I should code up a whole load of different transition operators and try all of them, because then I might be able to explore the space better. So in this particular problem, I realized that when this parameter takes on a value between 0 and 1, my model tends to do one type of thing. And when the parameter takes on values between 1 and 10, that tends to correspond to some other sort of model behavior. And I want my Markov chain to make sure that it spends lots of time looking at both of those model behaviors. So I've decided to create a Markov chain transition operator that deliberately moves myself between those two regions a lot. And I'm going to mix that together with other transition operators that are more standard that will explore the whole space for me. So this transition operator says, if I'm in the first region between 0 and 1, I'm going to multiply my current state by 9 and add 1. So if I'm currently here at 0.8, I will sort of go to 9.1 or whatever it is over here. And if I was at 9.1, I follow the second rule. I take 1 off my current state and divide by 9, and that will teleport me back to somewhere in this region. So this move by itself can't sort of explore the whole state space, because if you're currently at a current position, it will just ping you back and forth between two particular states. But if you combine this operator with other things, that's fine. You don't have, each individual operator doesn't have to be ergodic. Okay, and then this is an arbitrary proposal mechanism. There are other proposal mechanisms you'll hear about, like Hamiltonian Monte Carlo, where you run some complicated deterministic dynamical system that take you from one place to another. And in Hamiltonian Monte Carlo, the papers say this is a Metropolis proposal, and so you accept or reject it using the Metropolis rule. So you accept or reject the move with this probability. So you evaluate the probability of your final state and your initial state, and then if you have this deterministic move moving forwards and backwards, then these probabilities are 1, so they cancel, so you just use this rule, and that's totally wrong. So the reason this is totally wrong is, imagine that my target distribution was a uniform distribution. So if I drew a point uniformly between 0 and 10, and then applied this operator, 9/10 of the time I'm going to be on the right-hand side, and then teleport into this region over here. And 1/10 of the time I'll be here and teleport to this wide region over here. So if I draw a sample from the correct distribution, uniform, and run this transition operator for one step, I'll end up with 9/10 of my mass over here in this thin region and 1/10 over in this really wide region. In other words, a non-uniform distribution. And so this operator is clearly incorrect. It doesn't return me another sample given a sample. So what have I done wrong?
I think it's the same case as in the beginning with the delta function, so you multiply by 9, which changes
right. So the bit where there's a delta function here, the arbitrary proposal mechanism Q is a delta function. It says that xt plus 1 is the delta of xt plus 1 minus 9xt minus 1, right? And this density of the delta function is infinity, and I have infinity over infinity, and they're not the same infinity, and I can't just cross them out. So you are able to do proposals of this form, but there's a Jacobian correction that you need to include in the acceptance rate, and you have to be careful. So when you read some papers that use fancy mechanisms like Hamiltonian Monte Carlo, they say things like, this deterministic transformation we're doing maintains phase space volume. And people who don't come from a physics background go, what on earth does that mean? And what it means is that they haven't stretched the space out so that they can just cross out these things and only look at the ratio of the final state and the initial state. So if you're ever coming up with some clever way of moving from one point of the space to the other, if it's a probability distribution and you can evaluate it, it's fine. If you're coming up with some deterministic move, then you have to be very careful. Okay. I'll finish there. The meta summary of my 3 talks is the way to do probabilistic modeling is you write down the probability of everything. If you can do that and you can evaluate it, you can run Metropolis-Hastings or other simple algorithms. So you just condition on the things you know, and then you sample everything else that you don't know, unless you can integrate some of it out analytically. And that gives you a walk process that steps through plausible explanations. It will say things like, I don't know where your dark matter halos are, but they could be here or they could be here, and you're sort of going to have to take into account all of those possibilities. Or if you have a regression problem, it will say, your trend surface could be in any of these places. In this region of the space, I'm confident I know what's going on. In this region, I'm really uncertain, so maybe you should do another experiment there, and you can do intelligent experiment design and that sort of thing. 3 minutes for questions. Thanks very much.
Can you give a quick example of how combining the transfer methods could work?
Can I give a quick example of how combining transition operators work? So Gibbs sampling is kind of an example of this. So in Gibbs sampling, you go to each of your variables one at a time, and you update just that variable. So if you have d variables, you could think of that as d different transition operators. One of them only updates variable 1, and it knows how to do that. The second one only updates variable 2, and it knows how to do that. And if you only ever ran the update variable 2 operator, you'd be in trouble because you'd only ever change variable 2. But if you concatenate them all together, then you can explore the whole space, or you can randomly pick them and eventually you'll explore that whole space. You might decide that axis-aligned updates aren't good enough, and you need to be able to move diagonally as well. So you could add extra operators that can move along diagonals and add those into your mix. So that's probably the simplest example. Yep.
The other updating, wouldn't it be easy to just write an algorithm when you have probabilistic updates which have the same algorithms as me? I'm not sure if I got that right.
Okay, so there's a question here of if I didn't do the delta function, but I used something like a Gaussian distribution with some width, wouldn't I have the same problem? So I'd encourage you to work through this for yourself and understand why it happens. So if you if these deterministic equations give you the mean of a Gaussian distribution, and you use that for a proposal and you do it carefully, you'll be fine. Simulate it and check that it works. And yeah, I think I'd just try it. Oh,
A little gift.
thank you very much.
Little gift from Anthony.
It's been a pleasure being here.